Okay, so we talked about inductors and inductance. Now, the other important elements that we are going to deal with in our circuits is capacitor, based on the concept of capacitance. Now, I'm guessing you might be familiar with this concept from your electricity physics courses. But the similarity between the equations and concept of capacitance and inductance actually makes it easier to remember and figure out the problems. For example, we learned about inductance and inductors that they are elements which have the capability, which have the ability to store store magnetic energy. Now, in the same sense, capacitance is the ability of an element to store electric energy. So magnetic, electric. Now, if you remember the definition of inductance, it was magnetic flux divided by current. Now, for capacitance, it becomes electric charge divided by voltage, okay? This similarity, they are not exactly the same and they are not exactly the opposite of each other. It is called duality. So whatever is given to you in inductance terms or inductance concept can be easily changed into capacitance concept. For example, everything magnetic becomes electric, everything in terms of voltage becomes current, current becomes voltage, these cases, okay? You'll see what I mean. So the ratio of total charge divided by the voltage will give you the capacitance. Now, if you are already familiar with capacitors, you know that the most basic form of a capacitor is two conductor plates, as you can see, with area of A, and there is some insulating material between them, which is usually called a dielectric. And that dielectric has a spacing of D, a thickness of D. Now, this equation can be used to find the capacitance of any structure that is in this form, which is called a parallel plate capacitor. If you have the area or the cross-sectional area of the conductor plates, the distance between them, and also the material that is covering the spacing between them, then you can find the capacitor value. Now, epsilon in that equation is something called permittivity. It's talking about where it is coming from. It's well beyond the scope of this course. And usually this equation is not given on the exam. But I mean, it's fair to say that it doesn't hurt if you just learn what it means. It means that, for example, if I double the size of the area of the plates, my capacitor will be doubled. If I double the distance between the plates, my capacitor will be halved, right? So on and so forth. Okay. One more conceptual thing about capacitor is that we usually have two types of capacitors in practice, in experiments. A class of capacitor is called generic, meaning that however you put them in you place them in your circuit, with whatever polarity that it's your choice, okay? You can put it like this way or the opposite way, it doesn't matter. You're going to get the same result. But we also have a class of capacitors called electrolytic or polarized capacitors. And if you put them in the wrong direction, with the wrong polarity in your circuit, they will be permanently damaged. They will, there's a chance that they will blow up if they are very large and you are very focused on your circuit, you're very close to your circuit. There have been cases of people going blind because there are a lot of chemical inside those capacitors that can just spill over your face or your shirt. Or so yeah, if you put a electrolytic or polarized capacitor wrong way in your circuit, it will be permanently damaged. Now, should we worry about that in this course? Absolutely not, because you won't get these, okay? Not because they are expensive, because we don't trust you, okay? So you don't have these capacitors in your mini labs, you get the safe one, the, I won't say child-proof ones, but maybe I'm going too far. Yeah. So let's just stay with the safe ones. And just look at the difference in symbols. We don't care about the symbols in our circuit analysis because we always assume that they are placed with the right polarity. I usually use the generic symbol, but even if I use the other one, that doesn't concern me, okay? You do your analysis exactly the way you do it with generic ones. The only difference is for experiment and not for calculations. Now, if you remember the second definition of inductance, which was actually a little bit more important, especially for electrical engineering, was that inductance is a measure of how an element, inductance, previous lecture, is a measure of how an element responds to a changing magnetic field, or in the parentheses, changing current. Now, if you want to change this based on the duality concept that I briefly talked about, the magnetic should become electric and the current should become voltage. And you get the definition of capacitance. Capacitance is a measure of how an element responds to the change in voltage or electric field. Okay? Let's talk in terms of formulas. Do you remember what was the formula for the inductor? For governing the voltage-current relationship of an inductor. V equal to L di over dt, right? Now, can you tell me what's the dual equation? Instead of V, write I. What should we write instead of L? C, because the inductors change to capacitor. And instead of di over dt, we write dv over dt. You get the equation for capacitor, okay? C dv over dt. Let's compare capacitor and inductors. Okay, in less than 5 seconds, tell me the relationship between the 4 quantities to the left circuit. So IT is equal to V1 minus V2 divided by R. If you don't want to answer for any reason, it's perfectly fine. But if you don't know how to answer that, that's a very serious problem, okay? If you don't know that one. Similarly, I can write IT equal to V1t minus V2t over C, because capacitors are exactly like resistors, right? No. Ohm's law doesn't apply to capacitors, okay? The one that you've written is Ohm's law, and it's wrong. So what's the correct equation? IT is equal to, you can pick C times derivative of, what is the voltage? V1 minus V2. Okay? That's the equation relating these 4 parameters. One more thing I forgot to say, that this equation, the main fundamental equation of capacitance, is only valid if current enters from the positive terminal. If it enters from the negative terminal, your equation needs an extra negative sign, okay? Any questions so far? Now let's talk about units of capacitance. How do you find a unit of some variable, some quantity? You write the equation for that quantity. For example, what equation do you know for C? The first one that we talked about in the previous page was Q over V. Give me another equation based on the boxed value, based on the boxed equation. I over dV over dt. And I can write this as I dt over dV. Do you agree with that? Now let's talk units. Do you know what's the SI unit of capacitor? No, the S I want.
Oh, farads.
Farads, okay? And farads is equivalent to what? Coulomb per volt or amp second per volt, right? Any problems so far? Let's find the current in this circuit. First, what's the voltage across the capacitor? 2 volts, right? So I'm going to write as V equal 2 volts. So the current IC is equal to C dV over dt. C is 3 farad. D over dt, 2 volts. It's equal to 0. Does that remind you of something? In case you've already studied the inductance lecture note. In DC circuits, inductors behave like short circuit. Can you give me the dual statement about the capacitor? In DC circuit, capacitors behave like open circuit. Okay? Now, did I just say that because of duality, or I can say because of that? Both. Okay. How do you go from this to capacitor being open? It's obvious. What is the current value? 0. In a DC circuit, the current passing through the capacitor is 0. What does it mean when the current is 0? It's open. Okay? So, in DC circuits or time-independent sources, with time-independent sources, capacitors behave as open circuits. Any problem? Brett? No? Okay, let's find the current passing through that capacitor when the voltage across the capacitor is given to you. So what should I do? Exactly. The capacitor value is 3. So I'm going to consider this plot piece by piece or piecewise. So between 0 and 1, dV over dt is equal to what? The slope, right? Which is equal to 2 minus 0 divided by 1 minus 0 is equal to 2. And hence current is equal to 2 times 3, which is 6 amps. T between 1 and 3, dV over dt is equal to the slope in this interval, which is 2 minus 2 divided by 3 minus 1, which is 0, and so IT is equal to 0 amps. And for T between 3 and 4, dV over dt is equal to a slope, which is equal to 0 minus 2 divided by 4 minus 3 is equal to negative 2. So your IT is negative 6 amps. Problem? You know how I got from 2 to 6, right? Multiplying by the value of C. So let's plot that. 1, 2, 3, 4. That's 6 amps. And negative 6 amps. Okay? A very important question. Can the current passing through a capacitor change abruptly? Someone answered it. Yeah. See, is the current changing abruptly? Is there something wrong here? Do you see anything abnormal? No, because the voltage is very well behaved and very student friendly, right? So there is nothing wrong here. So I want you to remember, for capacitor, what cannot change abruptly? Voltage. For inductors, how about inductors? Current. So voltage for inductors and current for capacitors, they can change abruptly, no problem. For example, for resistors, what quantity cannot change abruptly? Fair. Yeah. Both voltage and current actually can. They are allowed to change abruptly. There's no problem with that. Okay? So let's see what happens if the voltage across a capacitor changes abruptly. So let's find current. What's the slope between 0 and 1? 0. What's the slope between 1 and 3? Sorry? Again 0, right? What's the slope for t greater than 3? 0. Is this characteristic fully representing my current? Not really, because it's missing 2 points, and they are very important points. At t equals 1 second, what's the slope? Positive infinity. And at t equals 3, what's the slope? Negative infinity. So, what does it mean, the whole thing, the whole example? It means that if the voltage changes abruptly across a capacitor, the current at some point goes to infinity. That would be very good, actually. We could use that for many purposes, okay? But unfortunately, that's not going to happen. Okay? Yeah, it's impossible. So, very similar to the example. Yeah?
Practical way of putting it, would this be like your startup draw on any kind of machinery?
Would it be like what?
A startup draw on a big machine, how it has a massive surge whenever you start, going from 0 to whatever the working voltage is?
Yes, if that happens in a short amount of time, yes. But anyway, it's not abrupt. It's in a short amount of time doesn't mean that it's abrupt, right? Yeah. Now, okay, so the voltage of a capacitor cannot change abruptly. Now, this is something that probably you don't have in the pre-notes that I uploaded to Canvas. I just added that today. I want to ask you a question. So, we established the point that the voltage across the capacitor cannot change abruptly. Now, look at that simple circuit. 1 farad of capacitor is connected to 5-volt voltage source. Now, I instantly turn off my voltage source. Okay? This is my question. If I turn off the voltage source instantly, unplug it, what's the voltage across the capacitor right after unplugging? It stays the same, 5 volts, right? You all agree. We just established that. The voltage cannot jump. So right after unplugging, it's going to be 5 volts again. So, very good. VC is equal to 5 volts. Right after unplugging five volts. Now here is the confusing part. Do you agree that I just unplugged the voltage source? So unplugging a voltage source is equivalent to short circuit. So do you agree that right after unplugging, this is my circuit? Or you have a problem with that? Okay, so if that is my circuit, right after unplugging, the voltage across capacitor, how can it be 5? It's short, it should be 0. Because? I don't know what energy is. I'm illiterate, okay? This is my question. You just said the voltage across the capacitor is 5 volts. And I accepted that. But here, if it is short, then the voltage should be 0. It cannot be 5 and 0 at the same time.
It will have a current when it discharges. So you have like a change.
Maybe you're right, maybe not. This is not my question. My question is, how can it be 5 when it is short circuit? Because capacitor what? Okay. Under what condition capacitor behave as short circuit?
Time.
Open circuit.
Time.
But this is not time independent. You just changed the voltage source from 5 to 0. So that's change, right? So it's not DC. It's called pulse. It's not DC.
Voltage can't abruptly change resistance.
Yeah, we established that fact. That voltage cannot change. So it should be 5. But at the same time, I've turned off my voltage source. I've unplugged it. It means that it's short circuit. So it should be 0. So which one is it? Is it 5 or 0? Why?
Because it's like its own battery. It just has.
Okay, but do you see that wire?
But even if you have a voltage source there, it's still 5 difference across it, right?
Even if what? Say it again.
I just said if you had like a voltage source there as like a 5 volt potential.
What happens if you connect the two terminals of a voltage source together? If it is too big,
It could explode.
yeah, you'll probably end up seeing your creator, right?
Or melt something.
What happens?
Energy is.
The current will pass through that, right? Is the current going to be a lot? Yeah, because it's a wire, right? But is the current going to be infinite? Why? Why it's not infinite?
It's not because the voltage is decreasing. Like whenever you like if you had a battery, like the voltage is going to decrease and it's going to go into that.
No, the voltage of the voltage source is never going to decrease. So let's assume that, I don't know, 1000 volts is a voltage source given to you. And you connect the two terminals with a wire. The current definitely is not infinite. We don't have infinite in nature. But it's going to be very high. Why it's not infinite and it's very high? Say it again.
It loses energy to heat.
Say it again.
There's resistance in the wire.
Is your wire zero resistance? No, it has some resistance. So the current is very high, but it's not infinite. Now put that aside, let's go back to here. As soon as I unplug the voltage source, what happens to the circuit? It gets replaced by only wires. But is my wire zero resistance? No. So I'm going to do this very small resistance. There's no violation anymore. Because, as you said it, as soon as you unplug your voltage source, you still have a wire around the capacitor, and it's not short. There is a voltage, 5 volts, and the 5 volts will cause a current to pass through the circuit. Can you tell me, this is probably next lecture, but it is good to ask you now. Can you guess what happens in this circuit eventually?
The voltage will continue.
Yeah. So, do you remember the most important property of inductors and capacitors? They store energy. So capacitor has stored some energy when it was connected to the 5 volt voltage source, and it hasn't. As soon as you connect the two terminals together, this voltage start pushing some current through the circuit, and that current will go and go and go until all the energy of the capacitor is completely depleted, completely discharged. Okay? So there is no violation. Just to make sure that my long discussion about this resulted in something. So as soon as I unplug the voltage source, what's the voltage across the capacitor? 5, not 0, 5. So let me write it. No, it actually looks like this. Okay. again, repeating whatever we talked about in inductors for capacitors. Like if you remember the integral equation that gave you the current of inductors when the voltage was given to you, this is the dual of that. Instead of current, I'm writing voltage. Instead of 1 over L, I have 1 over C. Inside the integral, instead of V, I have I, and instead of IT naught, I have VT naught. Okay? So exactly the dual of that. If you remember, inductors have memory, capacitors have memory. Inductors store magnetic energy, capacitors store electric energy. Okay? Let's do this and see what happens. So, which one is given to you? I. Can I use the main equation of capacitor? No, but because that was I equals C dV over dt. So I should use the opposite of derivation or opposite of differentiation, which is the integral form. So I'm going to write that here. Vt is equal to 1 over C integral T naught to T I T prime dt prime plus Vt naught. Okay? Piecewise, right? You've done this several times. From 0 to 1. Do you want to go for the end point of the interval, or you want to find the general function of the interval? Which one is easier? The end points. Can we use it here? Why?
Oh, because you're
Why?
Is it because the current changes over time?
No. Do you remember? Do you know what I'm talking about? So we had two options of doing integrals. One gave you the function, the general function of that interval. One only dealt with the final point of the interval. And then we ended up getting some points and connecting them. Now, can we go with the point method? Or we have to stick to the general function method? How? Because your current is fixed, constant. What does it mean? What's the integral of constant? Line. So you can easily connect the point. If you don't know what I'm talking about, that's not actually all my fault. Refer to the previous lecture. We talked about this in details. If you don't still accept that, refer to the start of the quarter when we talked about charge and current, okay? Integral in general. So let's stick to the end point of the interval. Can you tell me what is V1 based on that integral? 1 over 5. What is T naught? 0 to 1. What is current between 0 and 1? 0. What is the initial value? 0. So that comes out to 0. For t between 1 and 3, V3 is equal to 1 over 5. Integral, bounds of integral. 1 to 3. The value of current, 20 amps. The initial value, 0. Equal to 20 over 5 is 4, multiplied by 2 is 8. For t greater than 3, Vt is equal to 1 over 5 Integral from what to what? 3 to t. What's the value of the current in that interval? 0 amp. What's the initial value of that interval? 8 volts. Remember, the final value of each interval is the initial value of the next. So what is that equal to? 8 volt. The integral is 0, right? So how do you plot this? At 0 is 0. At 1 is 0. At 3 is 8. And after 3 is also 8. So, see, because this is constant, this is a constant function, I know the integral is a first order function. That's why I can connect them using a straight line. Did that make sense to everyone? Let's do something. Can someone tell me, okay. First of all, do you agree that this is the circuit representing this problem? This is IT, and this is C equals 5 farad. Okay? IT is exactly the plot that is given to you. Until 1 second, everything is 0, and the capacitor, nothing in the circuit. Now, at 1 second, current jumps to 20 amps. Okay? There's not problem with that. And then goes for 2 seconds and then jumps back down to 0. Okay? What happens after 3 seconds in the circuit, physically? Sorry? Yeah, because the current has come back to 0, right? So the current is 0. So there isn't any current source feeding our capacitor. What does a 0 current source mean? Open circuit. So after 3 seconds, do you agree that this is representing your circuit? Just a capacitor? Because the current source was became open, right? It's 0. Can you tell me what's the voltage across the capacitor? 8. Do you see anything interesting here? Anything useful? Voltage source is a good understanding of that. Well, you charge the capacitor, right? And after 3 seconds, you remove the source, but your capacitor is holding the charge for you. You've completely detached it from your circuit. See, it's alone by itself. You can put it on the table. It is still holding 8 volts. Okay? Do you see what we mean by storing energy? Like that. Now, what happens if I connect that capacitor back to a circuit? It will act like a voltage source. Right? We will talk in more detail on Friday about this. But so far, I just want you to understand why it can actually mimic a voltage source. Okay? Any question about this? Yes?
Could capacitors and maybe the other one, could they be used to measure like the other variable that's given by the source? For example, in this case, is 8 volts accurate to say that that's the voltage drop across the current source, or would it have to be more? What we have to do more to do that?
Well, they are in parallel, so it's definitely the same. Yeah.
So instead of having to like, let's say, 1000 resistors and capacitor, did that capacitor be used to measure the voltage drop across that resistor?
Well, not only used to measure the voltage, capacitors are sometimes used as voltage regulators. What does it mean? It means that they ensure the voltage across two terminals of some circuit stay fixed. Okay? Yeah. Yes.
So once like a capacitor is fully charged, just add like a broken wire.
With some superpower. Yeah. Yeah. Because it has voltage across it. A wire never has anything across it, right?
And it's like the opposite of inductors, because like inductors initially act like broken wires and then they let current pass through.
Yeah. Yeah. And also, now, since you not letting it go, let me ask one more question. What's the difference between a capacitor and a voltage source? A charged capacitor and a voltage source. That's useful for next lecture.
Capacitor doesn't require any power, like constant power.
The voltage source doesn't need anything else.
One is steady.
The voltage source will give you 9 volts or 5 volts constantly. But this guy, as soon as it's connected to some other circuit, the voltage drop across it start to fall off until it becomes completely discharged. Okay? Do you remember the equation for energy in inductors? 1/2 L I squared. What's the dual of that? What's the dual of 1/2? 1/2. C V squared, right? So that's the one. How did you combine inductors when they were in series? You combine them like you do with resistors in series, right? Now, how do you combine capacitors in series? You combine them like you do with resistors in parallel. You see? The opposite of it. So, if you have C1, C2, C3 in series, this is how you combine them. Look familiar? The parallel resistors. And if they are in parallel, how do you combine them? Just add them. Exactly like series resistors. Okay? Any problem?
And just to be like, just for clarity, that this formula is the same formula for equivalent resistors.
Sorry, I didn't get
It's the same formula for equivalent resistors, right? It's the same concept, like
For inductors or capacitors?
both and resistors. They all use the 1/1.
Yeah, exactly. Okay, see, I don't like giving students equations without proof. And I can say 99% of the time I haven't given you anything without proof. The reason I'm not following along these lines because they are boring and they are not required for your general understanding of the course. But if you are interested in them, you can always refer to the lecture note. See, just 2 lines of proof. And I have shown you why this equation actually holds. Okay? That's it. I'm done. Any question?